All right, class, let's try another video solution here. How about this one from Chapter 8, number 18. And it says this, Mercury follows an elliptical orbit that takes it as close as 46 million kilometers to the sun and as far as away as 70 kilometers from the sun. So if, say, this is the sun, the path of Mercury is elliptical. That means it's a little closer and a little further. So over here at its closest point, it is saying it is 46, and if you let me write it as a million kilometers, and over here it is 70 million kilometers. Okay. At both of these locations, Mercury velocity makes a right angle to the direction of the sun. If Mercury's speed is 38 kilometers per second when it is furthest, so let's say right here at its furthest point, it is going 38 kilometers per second. When it is furthest from the sun, how fast is it moving? So when it gets over here, how fast is it moving? Okay, so the idea here, and this is our third and final mechanics chapter, but there are three important conservational principles that I hope you're finally putting together. In chapter 6, there was conservation of linear momentum, and in chapter 7, there was conservation of energy, and now in this chapter, there's conservation of angular momentum. So as long as there's no outside torques, it'll keep the same angular momentum. So if I make two columns like I've been doing many times before, and I say call this the before and this is the after, so let's say over here is the before, we like to say then that whatever angular momentum it has at B, the before, it has again later on when it gets over here at A. So that's the principle of conservation of angular momentum. So we'll just calculate it here. And one of the formulas that we had was MVR. MVR. So what this is saying is the mass at point B times the velocity at point B times its distance that it is from the orbit, the object, which is the sun, B, is equal then to later on when it is at A, and A. Now, of course, since it's a planet, the mass doesn't change, which is mathematically means we can cross it off. And of course, the other good thing is nowhere in this problem did they tell us the mass of Mercury. So being able to cross that off is kind of nice, although it wouldn't take too much effort to look up the mass of Mercury. But it's kind of nice to recognize that we don't need it. Then on the right-hand side over here, I can put what they gave me. The velocity at this point is 38 kilometers per second. And the distance away, or the radius, is 70 million kilometers away. So there's the V and the A. And then on this side, you can see that the R went down to 46 million kilometers. So that means the velocity must go up. And so this is a calculation that hopefully matches the example you saw me in class where I was on that little spinny stool and I put my arms out and then I pulled my arms in and I kept pulling them in and out with the weights in my hand. And so that's what's happening here. The weight is going in, and so it would be going faster. And so that's what we're going to find here. All right, so to finish up the problem, we're going to grab our calculator here. So this is the 38,000, or I'll just do it in kilometers per second. So 38 kilometers per second. In fact, maybe I'll save myself a little calculator work and not only cancel off kilometers, but also a million. So that all I have to worry about is the 70 on this side. And then when I divide, I only have to divide by the 46. Okay, and so that comes out to be 57.8 kilometers per second. So conservation of angular momentum is the key to this problem.